the quiz. So before I start the slides, I just wanted to remind you that today at 2 p.m. The first assignment is due, and I hope that by now you have almost finished the material. And I will also post some tutorial material in the next few days. Next week we won't have lectures, so next week it's going to be off for all of us. And I will post some material, and I will also possibly email you some items related to the material that we have seen so far, or future additional material for your reading. I would like also, from the questions that I received, I mean, the numerous questions that I received by email or through Piazza, I would like you to be able to implement computer programs, whether on Pythons or on other type of tools that you can utilize. This is very important for you, and it is we are going to utilize even further these type of so let me check here. Oh, you are not hearing me. Let me check here. Do you hear me now? Yes, okay, thank you for letting me know. Thank you for confirming. Yeah, yeah, I would like you to accommodate yourself, accustom yourself with the programming environments. Mahmoud has put together a number of excellent tutorials to showcase you how to implement a program on Python. Things are going to become even more involved in assignment number 2 and assignment number 3. So I advise those of you who do not have a very deep background on implementation of the programming environment, please train yourself over the next few days or few weeks, so that when you get to the assignment number 2, you are ready to solve it without any issues. Of course, many of you, the majority of the students, I mean, have excellent material on excellent background material on programming, and I'm not worried at all. Okay, let me go back to the slides now. So let me go back. Before I start the slides, any questions, please? Do you have any questions? Okay, so let me go back to the slides. Please raise your hands or anything, I mean, or let me know through text, and I will be happy to respond to you. Today, as I mentioned to you, I'm going to finish up the material on the support vector machine, but I would like also to start the notion of unsupervised learning. So I hope that I have enough time to start the lecture on unsupervised learning, which we are going to tackle during this course, one of the most well-known unsupervised learning tool, which is known as Cohen's self-organizing map. So last time we spoke about, let me get the comment here, the thing, so that I am able to edit the file here. So this is the pencil here. Okay. So last time we said that for support vector machine, especially for systems of 2 binary classes, and I'm only going to showcase you here the system with 2 binary classes, how we are going to utilize them and how to use them, whether for perfectly classified, I mean linearly separable type of classes, or for classes that may have a certain type of overlap of 1 or 2 items that are overlapping in the opposing class, and I will explain that to you. So we are going to see the perfect solution for the original support vector machine, where we have 2 classes that are separated, and where we have some elements of the classes, such as a blue item here or a red item in this particular location. So what we mentioned in the last lecture, we mentioned that we would like to maximize this margin. This margin has to be maximized subject to the location and subject to the support vector. So these are what we call them support vectors. So they are elements that are at the extreme of every class here, binary class, of course, in this particular case. So we have these items here, this item here. It could be several type of items here. We call them support vectors. And here we have the same thing, okay? So we would like to locate this particular line here. And from either sides, we have a symmetric type of region, which we would like to maximize as much as possible. Why we would like to do that? Simply to improve the generalization of the classes. What we mean by generalization, it would like to have these type of separation as optimal as possible, so that whenever there is an additional point that belongs to either one of the classes, it's going to be situated in either one of the regions, and it has to be as distant from the other class as possible. So remember generalization, we discussed it before. It's when the system is able to classify in an adequate manner new elements that have never been seen by the designer. So this is what we discussed last time, and we try to formulate this particular representation in a mathematical manner, and we came to define this particular margin here as the element of 2 divided by the Euclidean distance of omega. And we said that the optimal problem here, again, I would like to remind you what we have discussed about machine learning problem. Machine learning problem, we said from the start, it is usually an optimization problem to minimize or to maximize a certain performance index. So here we come back to the mathematical formulation of this particular machine learning model, where we would like to minimize this particular performance index, which is the Euclidean distance of the half of omega t square, which we would like to minimize, subject to this particular type of constraint, which tells us that we have to be away from the margin, which is outside this margin. That's what that particular equation means. Okay, so the second equation means that we are away from the margin. So we would like to minimize omega t scalar product with omega, so that it maximizes the value of the margin m, subject to the fact that we are on either one of the sides of the classes. And this particular greater or equal than 1 reflects that some of the elements of these two classes could belong to this particular boundary, as you can see. So this reflects the equality to 1, okay? And greater or equal than 1 means that we are located here. We are located in this particular region, whether for class 1 or for class -1. So this is the bottom line. So we would like to optimize this particular performance measure. So last time I was talking about the xi and the yi. So the xi is legitimate here, and the yi is legitimate. So what is xi? Xi is simply the training pattern that we have subjected the system to. It could belong to class 1 or to class 2. And the yi is class 1 or class -1. Remember, in the early formulation of the system, we have defined a whole set of patterns, okay? And all these patterns are in the vector form. And each pattern has an input and has a category. The category, it's either +1 or -1. So this is the xi's, and I equal to I from 1 to L, and each one particular training pattern belongs either to one class or to the other one. So this is what we would like to do and how to solve it. We are not going to go into the technical details on how to solve for this particular equation. It's a little bit complicated, so it's not the time here to do it. But nevertheless, I would like to introduce you to what is known as the Lagrange multiplier when we have classic quadratic programming optimization with inequality constraints. So I'm sure that some of you have seen this type of optimization. So in order to put together these two types of elements, so this is the optimization metric that we would like to do, and this is the inequality constraint. So in order for us to join these two, we join them by what is known as the Lagrange multiplier technique. So we create the Lagrangian here, what we call the Lagrangian, and this Lagrangian is expressed in the form of the performance index, and also it is expressed in this particular format where we translate this particular format. So we take the one from the other side, so it becomes yy times omega t xi plus b minus 1 times what we call the Lagrange multiplier. So this is the formalism to solve for a quadratic programming optimization problem subject to inequality constraints. This is one of the techniques, actually. So there are a number of other techniques, but the Lagrange multiplier is one of the well-known approaches. So formulating our problem, going from this minimization to this, so basically in this element, so we would like to minimize this to increase the margin, subject to this particular constraint to tell us that we should be away from the two classes themselves. We are only going to touch it by one or few points, which we call them support vectors. So this particular equation, we are not going to go into the details of how to solve it. I mean, in all optimization problem textbooks or notebooks, I mean, you find them there. And I'm going to give you very quickly the solution of this particular problem using what is known as the Karush-Kohn-Tucker conditions for the system. We design this particular problem and we form what is known as the dual form of optimization, which is given by this particular format here. So this is the dual form, such as this particular type of condition. So we go from this particular problem, which we'd like to solve here, to the dual form of optimization problem to solve it, which is much easier than the other problem. And these type of problems are going to provide us, I mean, for these particular values. So we are going to solve for the omega 0 and also solve for the B0, because those are the solution that we are aiming for. Remember, omega is this particular element. So omega is this particular type of vector that we would like to find, such as when it's, scalar product with x plus b. So we would like to maximize this margin, and the maximization of the margin provide us with the minimization of the Euclidean norm of omega. And the value of omega 0 that is going to solve. So this is the gradient. As you know, this is the gradient, as we have done it in the gradient descent for the machine learning problem. And this is going to be given by omega 0 that is going to be expressed by the Lagrange multiplier times the class and the exemplar that we have chosen. So this is the summation for all the type of elements. That is what is the solution for this particular omega 0. And the alpha I is going to be solution for this particular equation that we have extracted from the Karush-Kohn-Tucker condition problem, where we have defined the dual form optimization. So alpha I is going to be this particular positive number, and it's going to be multiplied by yi, xi. We know what is the yi, we know what is the xi, and then also we have the b0 is going to be equal to 0, and this is going to provide us with this particular type of equation here to solve for this particular type of problem. So this is what we call the dual problem, which is a globally optimal solution. And the various values of omega are going to correspond to what is known as the support vector for our solution. So that's basically what is the solution of the support vector machine that we are going to utilize here. And it provides us with the value for omega 0, and also it provides us with the value of B0, which we would like to extract for this particular problem. And B0, as you remember, provides us the direction of where that line is going to be located, the line in the middle of the margin. Okay, so this is the original support vector machine problem. So when we speak of original support vector machine problem, it means that we have class 1 here, we have class 2 here. They are far away from each other. And then we are going to provide, with boundaries. So let's increase this one to make the support vector. And we are going to provide for this particular margin. And we are going to provide for the direction of the vector and where the vector is going to be located using the value of B0, and provide us with the weight vector, if you would like to call it, that is going to provide us with the various type of elements. As you can see, these particular elements are given by xi's and yi, summation of all the particular element, and it is a vector, as you can see. So omega 0 is a vector in the 2-dimension space or in the n-dimension space, depending what is the dimension of xi. Remember that omega and xi have exactly the same dimension because each one of them is multiplied by one component of the other one. So this is the solution for our particular problem for this conventional or the standard optimization problem for support vector machine. So it gives us the value of the vector omega 0 and the value for B0, which actually provide us with the location here. So as you can see here, the B divided by omega. So knowing this element, it provides us the distance from the origin to this particular type of vector. And also it provides us with the value of the margin, which is given here by 2 divided by omega. So the highest level of the margin is going to be given by 2 divided by omega 0. And omega 0 is the optimal value of omega 1. So that's our margin, and B0 provide us with the direction that is going to be locating the vector here. So knowing the direction of this particular line, knowing the margin value provide us exactly with the location and with the width of this particular margin and its supports for the support vector machine. So that's the mathematical framework. So we started with that minimization problem. We went to the Lagrange multiplier technique. We used the dual form of optimization problem to provide us finally with the solution provided by omega 0 and B0. If we are solving for omega 0 and B0, then our problem is going to be solved and the problem is resolved. There are many type of tools that are utilized for solving the original support vector machine type of problem. Okay, let me take a few questions here, if you have any, please. Hello? Do you have any questions so far? Okay, so if not, let's continue with this particular problem here. So let me go to page 15 here, slide 15, before I go back to slide 14 to formulate the problem. So sometimes when we have a certain type of classification problem, we are confronted with a number of items. Some of the times, you find out that one particular item that belongs, so let's suppose that this is class 1 and class 2. One particular item belongs to class 1 is located in the depth of class 2. Again, this is in the 2-dimension. We can extend this to multi-dimension type of representation. So what should we do in this particular case? Should we try to find, very complicated type of boundary that has to encompass this particular element so that it makes it belonging to this class? Sometimes we say no. Why? Because a lot of the times when we have this particular measurement, this might be due to the noise of the sensor. Remember what we said when we are observing particular type of data or when we are collecting certain type of data, then usually the problem is mostly due to sensory type of behavior of the system. So the model is not able to accommodate for that. So what we are going to do, we are going to accept this particular type of anomalies, if you would like to call them. It could be 1, it could be 2, it could be a little bit more than a large number. So we are not going to sacrifice an excellent type of boundary that we found between the two type of margin so that it belongs to one of the class or to the other one. So what we do there, we are going to tolerate this type of margin, and tolerate it by, call it, instead of hard margin, as we saw in the standard support vector machine, we are going to tolerate it using what is known as the soft margin. So our margin is going to tolerate some type of data that sometimes might be existing in the other class. Okay, so how to define this problem? So simply by adding this slack variable, what we call it, the zeta I here. Okay, so the remainder of the formulation is exactly the same. So we have H1 of the first boundary, H2 of the second boundary, but we are going to tolerate some type of elements that belongs to the opposing class. So this provides with the relaxation of what is known as the relaxation of the constraints of our system. So now going from the standard support vector machine to the more relaxed type of representation, which is soft margin. It's not a perfect margin, but we can tolerate sometimes data that we know it belongs to the other class simply because of noisy measurements, simply because of anomalies in the observation type of tools that we have utilized for that particular system. So we are tolerating this element here, and as you can see, its distance, its location with respect to this particular line, that is the center of the margin, is going to be given by minus zeta divided by omega. Omega, again, this is, the Euclidean distance of omega, which is the vector that we are utilizing here, which is scalar product with the x input for our system. And the formulation becomes simply the usual minimization of this term, but now we are adding this particular slack element. So what we try to do here, we would like to minimize this element and also this particular element. So we would like to minimize this particular element, which we saw earlier, but also we would like to minimize this particular element subject to this particular of slack. Okay, so this slack is again denotes where the data is located with respect to another in another position of the other type of class. So this is what we call soft margin of support vector machine. So whenever you hear this word, it means that we are allowing for some data to belong to the other class. Okay, and so this is a misclassification, but sometimes we are willing to accept this misclassification. So this is what is known as the softening of the classifier. Okay, so the higher is the value of C, the less tolerance support vector machine has for misclassification. So the more we put more constraints on this particular element, the more we are tolerating less. So we are becoming very, very rigid with respect to the tolerance of these type of misclassification. So we tolerate less the misclassification of the system. So if you would like to tolerate as much as possible the system, so put C as very, very small elements. Okay. However, if you tolerate less, you have to increase that second element for the optimization performance index. The same thing here for the performance index of the inequality constraint. We are going to utilize 1 minus zeta I, which means that we are within that particular slack that is defined by the zeta. So the zeta is defined by this upper element of this particular distance between these elements and this particular location. Okay, so we are going to do the same type of solution here. We are not going to work on the development of this solution, but this problem has been solved early, and it is called what is known as the primal problem. So the primal problem is no other than the dual optimization problem of the Lagrangian type of equation. So that's what we call the primal problem. So the primal problem gives us, representation similar to this, similar to what we saw earlier. So this is the dual representation here, and this is subject to the product of alpha I times omega I, and C is being the elements that we would like to optimize to tolerate high or low the misclassification of the element. Okay, and this is basically the solution for the system. So, so this is the primal problem solution here, and this is the dual problem that is provided by these type of equation in here. Okay, so we are not again going into the solution for this particular problem. We are going to utilize the Kahunen condition, Tucker condition problem by having dl with respect to d omega equal to 0 and dl with respect to db. So still, we would like to find out how to minimize this dl with respect to this omega and how to obtain this particular value for the b. So we would like to have these gradients are equal to 0. So the solution for that particular problem is provided by the dual problem, which is mentioned in this particular representation of LD. So D stands for dual here, and this is subject to alpha I times yi is equal to 0, and of course alpha I here is not only positive, but it is constrained within the limit between 0 and C. So this is a little bit more complex problem than the standard support vector machine, and the solution, as you can see, is even a little bit more complicated. So I wouldn't worry about this kernel here. So this, you can imagine it. So this kernel here at this particular stage is equal to xi t times xg here, okay? And we represented here the kernel. We are going to see it in a few moments. The kernel is basically no other than a trick that we are going to use later on for change of coordinates. So this is the most general type of equation that we have for this particular problem. So if we go back, okay, so this is the primal problem, the Lagrangian problem, the one that we defined in the earlier slides, minus this particular element, okay, subject to this particular solution. So the difference with respect to the primal problem of the original support vector machine, in the other problem we did not have the C, we did not have the zeta, and we did not have the zeta. So it's exactly the same formulation. So this, we can look at it even the more general case of the primal problem, and this is the more general solution for the problem for support vector machine. So the soft margin is the general case, if you would like it, to the standard problem that we have defined in the earlier slides. Okay, so these are the final solution for the soft margin of the system. So we have omega 0 and we have b0 provided to us here, where all the elements that we defined earlier stands in this particular solution for this particular system, and this particular summation. So we have seen this NSV here. So this, what we called earlier, let me remind you. So this is what is known as the number of support vectors. Okay, so the number of support vectors, we defined it earlier here, and we come back here and we find it here. So for the support vector for the, for the binary system in the 2D, that number is equal to 2. If we have other type of elements for the support vector, so that number might become even larger. Okay, so the decision function is given, what we call it here, the decision function for the system is given here by some of the elements that we have defined in this particular representation, and it gives us the way on how to represent these particular type of kernels that we introduced earlier. So this could always be looked at as xi times x. Okay, and this particular decision function provides us the boundary within the location of those type of lines that provide us with that particular type of margin. So, but this is the more important component that I would like you to remember here. So we have the omega 0, we have the B0 here, and these are the type of solutions that are able to solve for this particular problem. Okay, so let me stop here for a few minutes, if you have a few seconds, I mean, or 1 minute. And if you have any questions over the past development, I will be happy to hear them from you. So to summarize, we want to develop the margin for support vector machine. We want to develop the soft margin for support vector machine. When you hear soft margin, it means that we are tolerating elements of the competing class on one of the other classes. So that's what it means, soft margin. So we can tolerate, for instance, we have 100 points belong to another class, and 1 or 2 items of that particular class belonging to the other class, and we are able to tolerate them. And still, we would like to come up with the representation of that margin that is going to separate between 2 or more classes. So that's what we defined. We have utilized the Lagrangian representation to formulate the optimization problem, which is an inequality constraint. And we found the solution for the standard support vector machine. And we have now solved for the problem related to the soft margin, which is where we have a slack element given by zeta s here in this particular element to tell us that some elements belongs to the other class. Okay, so I'm going to go next to a very important component of support vector machine, which is going to define what we mean by kernel and how to change the particular representation of the support vector machine from the linearly separable type of data to data that is not linearly separable, but still with the change of coordinates, we are able to do it. So let's look at this particular slide. So what these slides tells us? So these slides tell us that we have in 1D dimension, we have some class C1 here and class C1 here, and then we have class C2. As you can see, over this particular line, which is not in the 2D, it's in the 1D, we have C1 here, and we have C1 here, and we have C2 here. So these C1 and C2 cannot be separated by a margin, cannot separated by one single boundary. So this is a non-linearly separable problem. So we need more than one Adeline, more than one perceptron. We cannot utilize the support vector machine as we have seen it in the past few moments. So we need a little bit more than that. So what we do here, we are trying to expand from this particular dimension. We would like to see if we are going to expand to another dimension, what would happen? So here, the two classes cannot be separated. So because we have another class here, so they can be only separated with two boundaries. Okay. But in this particular case, when we are doing it, you can see how this class now belonging to this particular area is now separate from this other class. And what we obtain also, there is the margin that we have defined earlier. So we went from inseparable classes to separable classes, and with a certain type of margin. And this, I mean, is provided to us because we have increased the dimension. So we are going to pay the price here. So instead of having the classifier in one particular feature space, now it's going to be in feature space X and feature space Y. So we are increasing the dimension of the data that we are separating. So instead of having one dimension of a class, now the class becomes of 2 dimensions, but we gain in terms of the classification capability. So the idea here is to map the data to higher dimensional feature space, along with using kernel, which we are going to discuss in a few moments. Let me remind you a little bit what we spoke about in past lectures. We said that in a lot of times when we would like to avoid the overfitting, what we do, we try to minimize the dimension of the input space, not increase it. So in increasing it, it makes the system more complex, the system more difficult to come up with the particular type of boundaries. In certain type of characteristics, in certain type of aspects, we may be allowed to increase the dimension of the feature space. And this is one of the cases. Why we would like to increase it? In order for us to create a separation between the classes. So the system provides us with better ability. And this is known as nonlinear support vector machine, which is the title of this particular slide. So why is it nonlinear? We go from linearly non-separable space to nonlinear separable space. So here, nonlinear separable space, why? Because we have adjoined to one particular feature another type of feature. And a lot of the times, this particular feature and this particular dimension are nonlinear in the original feature space. So instead of having dimension of x, so then we are going to increase it to x and dimension of, let's say, x squared. Okay, so this is very often when we are representing the type of support vector machine. I am posting alongside with this type of slides, I'm also posting some material to illustrate these particular factors, and I will even post a video clip to showcase you how we can go from a 2-dimensional type of system to 3 or even higher, so that the spaces are going to become separable by hyperplane. Remember that this is a line in this particular case, but if the dimension is higher than 2 space, then it becomes a plane or hyperplane if we go beyond the dimension of 3. Okay, so the idea is to map the data to higher dimensional feature space. So that's the main idea, increasing the dimensionality of the feature space, which are the inputs of the machine learning engine. All of this that we are describing here, of course, doesn't have any correlation in terms of the structure to an artificial neural network, which uses different type of structure, different type of architecture, known as the multi-layer perceptron system. So this is a support vector machine for which we would like to solve the problem using these particular type of boundaries. And why we are doing that? In order for us to solve for this particular problem. So for this particular problem to be solved, we are going to come up with what is known as the kernel. Remember early on, let me go back a few slides here. Remember this particular representation here, xti times xi. Okay, so this particular problem here, so this actually, this is not xi, so this is xj. Sorry, this is xj. Okay, so remember that this is the inner product of xi vector that has its class yi, and this is xi that has its class of yj. Okay, so these are the representation of this particular system. Now, if we are going to do a change of particular change of coordinates, so this xi becomes phi of xi. So instead of having the vector xi itself, so this phi xi is going to be something of this nature. So it's going to be xi, it's going to be xi squared. It could also take xi cube, depending on the change of coordinates of the system. So we go from one dimension of the vector space. I mean, we say dimension because xi could be a vector. It is a vector itself, to a multi-dimensional representation. So this is making it even more complex when we are going to do the change of these particular variables, the change of coordinate systems. But there is what is known as the trick of the kernel, because now if we are going to do the inner product of phi I times phi j of xj and transpose, this is going to give us to huge type of representation. Remember that this is a scalar here, okay? So this is scalar, all of it is scalar, but this is the inner product. So the inner product here becomes of dimension 9. It used to be of dimension, smaller dimension, of dimension 2 within the space of xi. Now it becomes of dimension 9. So this is going to increase the computation and makes it extremely complex. In order to do that, we utilize what is known as the notion of the kernel. So the kernel, what it says, the kernel, it is represented by this particular type of formulation here. So this xi times phi xj here, look at the phi x here. It's 1 xi square, square root of xi, xj square. So this is very high dimensional type of system. So this is T again, okay? So this is transpose. This is what we have it here, the correct one. So in order to do that, we are going to, instead of computing all these particular type of elements, these type of inner products, in this particular case, it's going to provide us 1, 2, 3, 4, 5, 6. So it's going to provide us with 36 elements. Instead of doing that, we are going to utilize these type of inner product system. And instead of doing all of this, we are going to do it simply in this particular format. So this could become represented by 1 plus xi times xj. So we go back from this increase of dimension to still play in the smaller dimensional type of space. This is what is known as the kernel function. So this particular kernel function that we choose, and which is equal to this one, which is legitimate, that we have to include it in the optimization problem, but its computation, instead of having it, I mean, phi xi times phi xj 1 by 1, this is going to be equal simply to this particular representation, 1 plus xi xj. And there are many, many type of kernel functions that have been utilized in the literature in such a way that it doesn't allow you, I mean, it prevents you from computing all these type of computation between one change of dimension to the other one. Instead of having 36 elements, we are going to utilize only the smaller inner product of xi times xj. And this is one of the major type of discoveries in the area of nonlinear support vector machine. Because when people made the change to deal with this particular type of transformation, they said, oh, now we are going to go with a very large number of computational elements in order to solve the problem. But then came the idea of the kernel, which we call it the kernel trick, which provides you with the equation within the system here, as you can see. Remember, this is what I said, this one, which is the equivalent of the xi times xj. And this kernel is a scalar that is going to be provided by that particular value without needing to change to the change of coordinates of the system. So this is one of the major discovery in the 1990s, and it provided us to create a decision function and to create the solution of the nonlinear support vector machine without having recourse to the large amount of computation. And the material that I'm going to share with you alongside with these particular type of slides is going to help you understand these even further, and it gives you some examples. Let me provide you mathematically what are the conditions for having this particular kernel. We are not going to get into the mathematics of it. So a kernel is a real valued function. As I mentioned, it's a scalar element satisfying what is known as the Mercer's condition. So without going into the Mercer's condition type of details, simply it satisfies this particular type of, this is the kernel type of representation. As you can see, it is very, very extensive, the computation. And this kernel could be only satisfied if and only if for any gx such as gx square x is infinite, then the kernel gx2 is greater or equal than 0. So we are not going to go into the details, but this provides you with the extensibility factor for this particular kernel to represent a higher representation of a particular type of vector when we are changing the coordinate system. So this is known as the Mercer's condition. Let me give you some examples of kernels. So there is what is known as the linear kernel, which is the easiest one to utilize. There is the polynomial kernel, which takes this form. It's similar to the one that we shown earlier, where similar to this one, where C is equal to 1 and D is equal to 1. So that's known as the polynomial kernel of dimension 1. There is what is known as the radial basis function kernel, and there is the sigmoid kernel. So now you ask me, when do you utilize one of those? So these type of kernels come when we start understanding the distribution of these particular type of data. So as you can see here, this is the linear kernel. This is what we usually utilize. So we don't need any type of transformation. This is second order type of polynomial. So when the data is separated by a simple polynomial type of order system, then we take the kernel as dimension 2. So here becomes to the power 2. So this is the usual one that we have utilized in the standard type of kernel function. And then if the data is a little bit more complex, fourth order polynomials that is separating between the type of data, then we utilize fourth order polynomial. This is eighth order polynomial. So the more we have bigger nonlinearity, the more the system provides us with these particular type of polynomials. So the radial basis function, the nth order polynomial come from experience about the type of data distribution. So you have to do a number of tests in order for you to apply them. So once we apply them, and once we apply the earlier type of solution that we have seen for the standard, the support vector machine, then we are able to solve this particular problem. So to summarize what we have just mentioned here, we are changing the coordinate systems by increasing the dimension. By increasing the dimension of the input space X, we are able to migrate from linearly non-separable type of space to a nonlinear separable type of system. And nonlinear separable system is provided to us by these nonlinear type of kernels. In forms of the computational system, the system doesn't change much in computation because we are utilizing the kernel trick. So the kernel trick is the kernel that you embed in the equation of the optimization, and it doesn't require us to compute all these type of inner product elements of the higher dimensional type of vector. So by utilizing these two type of things, the kernel trick, we are able to solve for the nonlinear support vector machine. This was one of the major discoveries in the 90s and in the early 2000s, and a lot of people have worked on this particular kernel machine. They are not connectionist, they are not based on artificial neural networks, they are supervised type of support, type of machine learning system. This is another class. I wanted to introduce you to this other class of machine learning system based on the support vector machine and the kernel representation of higher dimensional space. Okay, so that's what I wanted to share with you. The final slide that I wanted to share with you here. This is the wide range of kernel that people have utilized in the literature. So many kernels, I mean, wide range of kernel functions that could be utilized, and each one could be utilized depending on the separation that you feel for that particular type of data. So there are a number of tests that people do before they utilize support vector machine or even nonlinear support vector machine. And this type of tests provide you with the best possible kernel function to utilize for your particular problem. So I am going to stop here for nonlinear support vector machine. I'm going to take some of your questions if you have any, and then we will move to the next type of slides. Okay, so let me see this question by one of your classmates. So it says that I am a bit confused between good prediction and good learning between global and local kernel. Doesn't good prediction require good learning? Yes and no. So global kernels such as the linear kernel give a good prediction ability because I mentioned this statement. So let me explain this particular statement. Global kernels such as the linear kernel give a good prediction ability. Local kernels such as the RBF kernel give good learning ability. Okay, remember what we discussed when we have tackled the overfitting and the underfitting. Remember what we discussed when we talked about the bias. Remember we said that a linear fitted model between two types of class has low variance, but it has big bias. Sometimes we are accepting of a big bias because, I mean, it gives us a medium type of prediction system without overfitting. So if our solution requires a good balance between, I mean, an average bias and an average variance, then we utilize the simplest of the decision space. And the simplest, we said, remember at the time, we said it could be linear regressor, or it could be first order polynomial or second order polynomial. However, when we went to have high complex model for which the system might be overtrained, especially when we have small amount of data, then the system is going to memorize what it has been trained for, okay? So we don't want that system to do that. So what we try to do, we try to do certain type of generalization capability. We try to increase the number of data points. We try to even make the system less complex. So local kernel provide us with good learning ability, which basically it's related to almost the training equivalent of what we have seen in the artificial neural network. However, what we need to have, we have to have a good prediction, but at the same time, good learning. So the prediction in the form of the testing. So the system at the testing sites, the system should provide us with as good error as we are satisfied when we are doing the training. So the global kernel is used for high bias, sometimes medium bias. The local kernel, sometimes they overfit, and we try to be very careful on to choose the parameters of these particular type of system. So here, that's what we meant by the good prediction and the good learning. So if you would like to see it here, it's not good learning ability, it's good local learning in terms of the training type of data, okay? And going back to what we said earlier, we would like our system to have low variance, which means that the system has to generalize very well. And we would like also to have medium bias. We don't want the data to be far away from the, the training data from the testing data or from the original type of model. Does that answer your question? Okay, I hope so. So that's what we meant there. I will pose.
Hi, Professor. Yeah, I think I'd asked that question. So what I'm understanding is like if I use a good learning in this context means higher complexity of the kernel model.
Yes.
Okay.
That's what we mean by good learning. But you have to test. You have to test your system. So these type of radial basis function, these high polynomial type of things, they are what we call complex type of classifiers. So we have to, whenever we are utilizing a complex classifier, you have to be very careful. Simply do your training but try also when you are doing the testing to make sure that the testing error is as low as the training. That's what I am telling you here.
Right. Okay.
Okay.
Yep. Thank you.
Okay, no problem. Any other questions before we move to the next item besides the support vector machine? Because now I don't want to spend more time on the support vector machine. For those of you who are interested in the reading more material about what we have, so there is a number of additional type of slides. I'm not going to go over them. This is also the multi-classifier system for support vector machine. There are a lot of aspects in the area of support vector machine. So there is the fuzzy support vector machine for various type of presentation. Support vector machine, it's a whole area of machine learning on its own, okay? But I wanted to introduce them to you here in order to explain to you another, or to introduce you to another non-connectionist model. There are other type of non-connectionist models, such as the K nearest neighbor system, that are also very well utilized, and there are a lot of libraries, but because of the restriction of time, I'm not going to go over them. I will include in future tutorial some material about radial basis function implementation, about K nearest neighbor, so for your ease to use. And also for tutorial number 3, there is an example that Mahmoud has implemented utilizing support vector machine. Please look at it if you are interested in the implementation, or if I ask you in the future, assignments on support vector machine type of classifier or nonlinear support vector machine type of classifier. Okay, so that's what I wanted to share with you about support vector machine. It's a little bit challenging because there is quite a bit of mathematical background. I mean, I try to give you the major equations in this particular representation, but with the additional material that I am posting on this subject, I mean, you should be able to read more and to understand even further some of the concept I have introduced to you here. Okay. Okay, so let me go now to our next set of slides. So let me go here. I would like to view page display, single page. Okay, do you see the picture here? So, okay, so we spoke about neural network. We spoke about two major classes of supervised machines. One of them is based on neural network. The other one is based on support vector machine, which we just ended a few moments ago. Now I would like to introduce you to one class of machine learning system, namely the unsupervised learning models. Remember when we spoke about machine learning systems, we said that we have the major type, supervised, and then another major type, the unsupervised, and another third major type, which is the reinforced. The reinforced, we don't see it in this class because it's taught in 457C. I mean, some of you may have taken this class with Professor Mark Crowley, so I don't want to replicate that effort, but I would like to emphasize on supervised and unsupervised, and later on I will speak a little bit about semi-supervised, which has both, I mean, both of these particular aspects, and later on I will speak on deep learning system. So I would like to give you, I mean, in this course, as much tools as possible for you to tackle them when you are confronted with the prediction, with the classification problem, with the regression type of problem. And assignment number 1 should have been an excellent exercise. I know that it may have been a little bit tedious for you, for first-time implementers of these codes, but I am sure that once you put the time into it, that would be very, very precious type of tools. And that was my main intention behind assignment number 1. Okay, so the unsupervised, I'm not going to go over the associative memory-based system, which is, another class of unsupervised type of neural network system, which is known as the Hopefield neural network. But you may, if for those of you who wish to do it, in the textbook chapter that I have posted on the modules or on the later part of this type of slides, you should be able to look at them. But they are not part of the assignments. and they are not future assignments, and they are not part of these particular or the quiz system. Okay, so let me go here. So the Cohen self-organizing map is going to be the one that I'm going to study, while the Hopfield neural network is part of this type of slides. I'm not going to utilize it in this course, so this is not included. Okay, not included. But feel free to look at the material if you would like to have more reading. Hopfield neural network are excellent type of tools for solving what is known as the auto-associative memory type of systems, and it has also been used in a wide range of optimization problems. So I'm going to focus on one particular unsupervised learning system because it's quite self-explanatory, and a lot of students, I have taught this in the past. It's one of the tools of unsupervised learning that students can grasp visually the importance of unsupervised type of systems. Okay, so common self-organizing map, people call it KSON, other people call it KSOM, so it depends on whom to talk about, to talk to, or which type of textbook. I utilize the KSOM in my textbook, so there is one full chapter. Chapter 5 of my textbook on Cohen self-organizing map, and it belongs to the unsupervised learning networks. So this means that the network, unlike what we have seen so far in the multi-layer perceptron and in the support vector machine, these type of networks, they update their weighting parameters not based on a supervised label. Okay, so we don't provide a teacher to tell us whether the output of the system is correct or not, similar to the supervised network, or even for the reinforcement, which provide us with the signal to improve the rewards for the agents that is doing the classification. So in this particular system here, the system is going to cluster, to categorize itself according to the other type of features. And it is indeed, it's according to the features. It's going to classify it according to the input space. We don't have here an output space for which we tell the system it belongs to a cat or to a horse or to elephant in terms of the image, or it belongs to class 1 or class 2, or similar to problem 4. In the assignments, it belongs to one of 3 classes, class 1, class 2, and class 3. That's a labeled type of set of data. That's a supervised type of learning system for which you can utilize a number of machine learning systems, including, the support vector machine, or including multi-class support vector machine, which we haven't seen, but it could utilize the multi-layer perceptron system. So this is the major difference between unsupervised and supervised. And a lot of the times I would like you to remember this. In the supervised type of systems, we talk about classification, we talk about regression. If the outcome of the system is continuous, we talk about regression. If the outcome of the system is discontinuous, then you tackle, what is known as a classification problem. You have seen it in assignment number 3 in the form of problem number 3, regression, problem number 4, classification, and problem number 1, classification. And the other aspect, when we are talking about unsupervised, a lot of the time, we are talking about clustering. Clustering, how to assemble various type of items based on their representation, based on their features, based on their attributes. No one tells us that this particular class belongs to tomato or to apple. The system has to do it on its own. The system, of course, at the end of the day, is not going to tell us, once it classifies or clusters tomato, it clusters apple, it clusters oranges, it will tell us that this is orange, this is apple, or this is tomato. Unless we tell them that for type of fruit, of vegetables, for which their input is belonging to this particular cluster, we call it tomato. So tomato has this particular size, it has this tactile type of feel, it has this. After you do the clustering through a computer vision system, the system now goes to another type of secondary network to provide labels to this type of systems or a teacher to this type of system. So a rule system could go, if the cluster that you have made through this particular computer vision, if it has the red color, if it is tactile, if it is has, this type of tactile type of feel for it, then you call it tomato. So we can go through 2 or even sometimes 3 layers of networks. Okay, so here we don't provide a teacher or a network trainer to tell the system doing that. Only at a later stage when we would like to do calling, this type of object. So this is a picture that I have shared with you some weeks ago in the input signal. So the system doesn't have a teacher. So there is no teacher here. No teacher. Okay. So the system is going to utilize certain type of attributes from the input signal. Okay. Using a certain type of architecture. I put here multi-layer perceptron, but it's not a multi-layer perceptron. So this could be, the output of another type of network, which we are going to see in a few moments. Using what is known as an unsupervised based weight updating system. The system is going to cluster multi-objects, and it's going to cluster, this is as class 1, this is as class 2, this is as class 3, and this is as class 4. So it's no longer the visualization of the multi-layer perceptron that we are going to utilize. Remember the multi-layer perceptron, we have used it as a structure of a neural network for supervised learning. We are going to utilize here another type of structure. Okay, so this is a different structure that we are trying to use, and we are not comparing with any other type of teacher. So the teacher doesn't provide us with any type of signals. Okay, so one major feature of this particular network, so we are speaking about network here. We might speaking about a connectionist model, but it's completely different from the structure that we have seen in the past. So in this particular network, we are going to have several type of nodes that are going to cluster themselves according to certain type of training behavior. So the system at the end of the day will provide us, this is cluster 1. So I put it cluster. It's not class, okay? So cluster 1 here, cluster 2 here, okay? So different, I would like you to remember, class is mostly used in general for supervised learning. Clusters are used for unsupervised learning. I would like you to remember these type of connotation, okay? One major feature of this particular network is that the nodes distribute themselves across the input space to recognize groups of similar input vectors. What does that mean? It means that these type of nodes that have clustered themselves around a certain type of structure have responded high to a certain type of input to the system. So if the system, let's say we are trying to cluster the apples. So apples have certain type of characteristics, they have a certain type of color, they have a certain type of shape. So when we are representing them as input type of vectors, we are going to say that this is the radius of the sphere of that particular fruit. This is the color of that particular type of fruit. This is the tactile sensation of that particular fruit. So all these type of elements are input elements to that particular element, that the data set, the data point of the data set. So that particular elements, once we go through them, we are going to scan among all the inputs that are provided to us. And all inputs that are close to each other are going to be clustered to one particular class. All other inputs that have other type of features that are similar to each other are going to be clustered according to 2. So we don't tell them that this is an apple or this is a potato or tomato or whatever. So we are letting the system decides for itself according to what we call proximity or similarity of these particular elements. Another example that I would like to convey here, for instance, I mean, a little bit complex example, but that's how people do. So imagine that in the news in general, do you think that the news, when Google provide news or CNN provide the news, I mean, as a bulk for you, or they know you that you would like to have a certain type of preference for news on politics? Do you think that this is going to be manual type of things? No. This is basically a trained system, a system that has been trained in the past. And this system could be trained supervised or unsupervised, but usually, I mean, this system has been trained with a certain type of keywords that belongs to politics. As soon as several type of documents have a large number or enough type of numbers for a certain type of words that are keywords in the field of politics, and these type of documents have certain type of measure that is similar to each other in terms of the number of words that are close to each other, then we say, oh, document 1 belongs to politics, document 2 belongs to politics, document 3 belongs to sports, document 4 belongs to sports. Sometimes there are confusion between sports and politics, but usually, I mean, these type of news documents are clustered according to their contents. And their content, of course, I mean, I will mention this a little later, but their content are in the form of words. And words are elements of a vector that we are providing them as input elements. So this is what we call it competitive learning. So class 1 and class 2 are going to compete among themselves according to a similarity measure that is coming from the input space, and then they will provide you whether you belong to cluster 1 or cluster 2. And I have chosen the Cohen self-organizing map because it's very visual. So it provides us with a better, I mean, view of why these type of classes. And in assignment number 2, I'm going to include 1 or 2 problems about, unsupervised type of learning system. Okay, so let me give 1 minute here before we leave, or 2, if you have any questions on what we have seen so far on the Cohen self-organizing map before I conclude the lecture. Feel free to speak or feel free to chat. I mean, I'm looking at the meeting chat box here on Learn. This is as important as supervised learning system, but we are going to go through quite quickly because Cohen self-organizing map, it's not a very complex system to understand, and the algorithm is not very complex, but it gives you an excellent idea on how to do clustering for systems that are not that do not have labels. Okay, so that's the what we call it a competitive learning type of system. So nodes compete among themselves to assign a particular type of cluster for a set of data elements. Any questions? Feel free always to email me or to email my TAs again. And I thank you for your attention. And I will be happy to post additional material. So I will post additional material on the Cohen self-organizing network. And I remind you that today is the due date for the assignments at 2 p.m. this afternoon. Have a good day, have a good weekend, and I'll see you the week after next, and good rest. Okay.